Lesson 28 demo. In this class, we look at two powerful approximation techniques used in applied mathematics when a function is just too complicated and messy to work with. Let's have a quick look at the Geogebra File 3.9 for a sneak peek at a generalization of what we're doing in this section. So here's the file, and I've got some function graphed here, and your job is to guess what function this is. Let's see, it goes up to 1, down to -1, looks like it's repeating. It hits here at the origin, and it hits the x-axis at right around pi, and maybe right around 2 pi. So if you guess this is the sine function, that seems perfectly reasonable. So we're just going to keep taking a look at this thing as it goes up and down as expected. Nothing to see here, nothing unusual. This is decidedly not the sine function, although it does an awfully good job of approximating the sine function for a long time before it reveals its true nature. This is actually a polynomial of degree 49, not at all the sine function. I'll show you the equation for this polynomial, or at least part of it. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus etc. It goes all the way out to x to the 49th over 49 factorial, but this graph right here is not sine of x at all. It is just a polynomial. And polynomials are really easy to work with. They're easy to take derivatives of. We're going to learn later on this semester in a bunch in Calc 2 about antiderivatives, and antiderivatives are typically really hard, but for polynomials, they're really easy. And so the idea here for this section is that we're going to take a function that's hard to work with and approximate it with a polynomial, something which is really easy to work with. Consider the function f of x equals square root of 1 plus x. Let's build a linear function L of x that behaves similarly to f of x near x equals 0. So here's our technique. I'm going to draw a vertical line here in the middle of all of these blanks. So the left-hand side has only to do with the function f of x. So let's just start there. So first, f of x is given up here at the top as the square root of 1 plus x. But let's go ahead and rewrite that as 1 plus x to the half, because right below we're going to find f prime of x. So we know this is the power rule with the chain rule inside. So the half comes down, copy the stuff, 1 plus x, subtract 1 from the power, and then multiply by the derivative of 1 plus x, but that's just the coefficient of x, which is 1. And then what we're going to do in the next column is plug 0 in for the x's. So f of 0 is really just 1 plus 0 to the half, which is really 1 to the half, and 1 to any power is 1. And then in the next blank down below, f prime of 0, we're plugging 0 in for x. So again, we get 1 plus 0, that's 1. And then 1 to any power, including the negative 1/2 power, is 1. Times a half gives me, at the end of the day, half. Okay, completely changing gears now. We're going to start with a generic linear function. L of x equals ax plus b. Probably you're more used to seeing mx plus b, but it turns out using a and b instead of m and b is more generalizable for us for where we're going. So anyway, ax plus b is a generic linear function, and we are going to determine the a and b to make certain conditions true. So let's go ahead and take the derivative of that linear function. So the derivative of ax plus b is just the coefficient of x. It's a, right? A and b are constants, so the plus b disappears. And then in the next column to the left of that one, we're going to plug 0 in for x. So when we plug 0 in for this x, we get a times nothing plus b, so that's just b. And then we're supposed to plug 0 in to L prime, and that means plugging 0 for every x that you see, but there aren't any x's there, so that function is just constant. So that means that L prime of 0 is a. In fact, L prime of any number is a. Okay, so here is what we are going to do. We're going to take that line that we put right here in the middle, and we're going to get rid of it. And we're going to make this thing, the 1, equal the b. So I don't really like that I've written it that way. So we're going to make these two things equal. And then separately, we're going to make these two things equal. So all we're doing is just making equals straight across this invisible line in the middle. And in doing so, what we're really doing is making f of 0 and L of 0 the same, and making f prime of 0 and L prime of 0 the same. And so I'm just going to write those two equations. 1 equals b, and 1/2 equals a. Oftentimes, the equations won't be as simple as this, and you'll have to do work, like maybe both equations have both a and b. You know, maybe this would be something like a minus 3b, and this is a plus 2b, and then you have to do some algebra solving a system of equations, maybe using the substitution method. But in this case, the equations are really easy. They're both solved instantly. And so that means that our linear function, L of x, equals, remember, it was ax plus b. It's circled up there in the top right in red. So ax plus b is really 1/2 x plus 1. And that is a linear function, which in some sense is similar to the original square root of 1 plus x function. It's similar in that they both functions have exactly the same y value when you plug in x equals 0, and both functions have the same derivative when you plug in x equals 0. Number 3, here's how we built the linear function above. We started by making our original function and our linear function have the same value at a single x value. It's called x equals a there. Unfortunately, it's not the same a as in the ax plus b. X equals a is just saying a specific x value. So we made the two functions agree at x equals a, and next we made the derivative of our function and the derivative of our linear function have the same value at that same single x value, x equals a. That's it. We call this line, the one that's up there in the purple box, the linear approximation or the local linearization of the function at x equals a. In this particular case, the x value was 0, and that has to be given in the problem near x equals 0. Okay, for each x value given below, let's find the y value of the function f of x equals square root of 1 plus x and the y value of the line we found above. So that's, again, given by that equation. We'll round our answers to the nearest hundredth and use the calculator only when necessary. So for the first one, let's just do the first column, actually. Square root of 1 plus x when x is 4, when x is 3. So that's really the square root of 1 plus 3, which is the square root of 4, which is 2. But on the next one, I do think we're going to have to use a calculator. So this is now 1 plus 0.3. So that's the square root of 1.3, which we'll use the calculator, and it says nearest hundredth. So that's what we'll do. All right, about 1.14. And then finally at 0.04. So this is now square root of 1 plus 0.04, which is the square root of 1.04. And we'll type that one in and get our approximation. 1.01, so it's really close to 1.02. I'm actually going to write a few more digits here. 1.0198. I think that's what we had. Okay, so now let's compare those values with the values on the line that we found. Now the fact is, calculating these three values here, or at least the last two of those three values, was trivial because we had this wonderful tool called the calculator. But it wasn't so long ago when the calculator didn't exist. And so could you imagine trying to estimate, without a calculator, the square root of 1.04? It would involve a whole heck of a lot of arithmetic, maybe some trial and error. They did have processes, like step-by-step processes to approximate square roots and other common functions back in the day before calculators. But anyway, they were involved and they were laborious. So these things were only really easy to get because we had this tool in our hands. So imagine putting yourself back in a spot where we didn't have the calculator. If you had to approximate these square roots by hand, it would take an awful long time. Let's compare to using the function that we came up with. So in this case, 1/2 x plus 1, but plugging in the same x equals 3. So that's 1/2 of 3 plus 1. So that's 1.5 plus another 1, that's 2.5. Then we're going to plug in 0.3 in the next row. So 1/2 of 0.3 plus 1. Half of 0.3 is 0.15 plus 1 is 1.15. And then finally plugging in 0.04, 1/2 of 0.04 plus 1. Half of 0.04 is 0.02 plus 1 is 1.02. So the idea is that our simple linear function is supposed to approximate that square root function for x's near 0. And so when we picked an x that was pretty far away from 0, we didn't have such a great approximation. Y equals 2 is the exact answer. That's the quote right answer. And our approximation is 2.5, and that's not so great. But then we picked a number that was closer to 0, and 1.14 is the right answer, and our answer is 1.15. But remember, 1.14 was only easy to get because we had the calculator, and if you didn't, that would be a lot tougher to calculate. Whereas this 1.15 was a piece of cake. We didn't use a calculator anywhere on the right-hand column. And then we plugged in x equals 0.04. Square root of 1.404 would have taken a long time to get this level of accuracy without a calculator. But take a look at how good our approximation here is. The right answer is this 1.0198, 1.0198, and our answer was this 1.02. And they're only off by, let's see, tenths, hundreds, thousands, 2 10,000ths, less than 2 10,000ths off. And again, calculating this by hand was trivial. No calculators needed. On the next page, have a look at this graph. How does it relate to our work from number 2? Okay, so this first function, the bottom function, I should say, looks like a square root function. In fact, it is a square root function, but it's been shifted over 1 unit to the left. It is the square root of 1 plus x. That was the function we started with on the previous page. And then the top function is just a straight line. It is the function 1/2 x plus 1. And so what's the relationship between those two things graphically? Well, let's take a look at the point we were focused on, which was when x equals 0. That was given in this problem. And at x equals 0, these two functions have two things in common. They have the same y value, and they have the same derivative. That's how we built the L of x function. But in number 6, it says, what special line did we find? Well, that L of x is simply the tangent line to the red curve at x equals 0. Maybe we didn't realize we were finding a tangent line. This is certainly not the process we've used to find the tangent line, but we ended up with the tangent line. Number 7, the goal of this section is to be able to approximate y values of points on a curve with y values of points on a simpler function like a line. So that's exactly what we did. For example, when we plugged in x equals 3 at the bottom of the previous page, we went to x equals 3 on the curve, and we got the point 3, 2. And then we went to x equals 3 on the line, and we got 3, 2.5. And those were kind of far apart. That's not such a great approximation. But then we went to x equals 0.3. Let's call it right here, x equals 0.3. And then we went to the curve at x equals 0.3, call it right there. And then we went to the line at x equals 0.3, call it right there. And I really can't even distinguish the 2 points because at that spot, the tangent line and the curve are so close together. And that's why at x equals 0.3, our approximation was pretty good. And then we went to x equals 0.04, and our approximation was really good because the tangent line and curve were so close to each other at x equals 0.04. Okay, let's use our linear approximation to estimate the square root of 2. So remember, the function that we started with was this, and this was our linear approximation. So square root of 2 is equal to f of some number. Now you got to be careful here. You don't want to just necessarily plug a 2 in because you see a 2 inside the square root. If you plug a 2 for x, you'd actually get the square root of 3, which is not what we want. So what number do we need to plug in here for x to build the square root of 2? Well, you got to put it at a 1 right there. So that's how we get the square root of 2. And f of 1 is hopefully approximated well by L of 1. That's the same one that we just copied there. The line is supposed to be pretty close to the curve if we're not too far away from x equals 0 in this case. Okay, and L of 1 we can calculate. It just means plugging x equals 1 into the L function. So x equals 1 goes right there. So 1/2 times 1 plus 1, which is 1.5. And I can tell you that from the calculator, the square root of 2 is roughly 1.414. So 1.5, not a bad approximation. And again, if you didn't have a calculator, getting this level of accuracy, 1.414, would take an awful lot of time.